Hey guys, so I'm gonna record the part of the discussion that I wasn't able to complete today within class because time ran out. I didn't realize. Should be quick and yeah, that's my bad that I couldn't finish. From next week, I'm gonna be more concise. Okay, so we covered load. Now let's cover store. So here you can see um strw, and so w is word, which means like 4 bytes. So store means basically we're putting the contents from the register back into main memory, right? And then they're asking for little endian. So first we have to look at, okay, which data are we transferring from the register? So we can see that we're going to like X9, and then we're going to index 8, right? So we gotta look from the top. So here we start here, which is at 0, right? So if we want to go to 8, we have to be like 0, 1, 2, 3, 4, 5, 6, 7, 8. So we end up here, and from here we're taking these 4 bytes. So, and this is the place where we're gonna store the data. So where are we getting the data from? We're getting the data from this X11. So, and then this is gonna be store word. So it's gonna be 4 bytes. And then we want to take the data that is at the little end. So that means the least significant end, the least significant bit side. So it's gonna be, as we talked about today, little endian is the rightmost side. So we're gonna take the four bytes from the rightmost side. And then we're gonna put it in the register just like that. So the highest data was at the least significant byte, so we're just gonna kind of fill in those blanks like that. So we go from bottom to the top. So that's little endian, like storing, and then this is the opposite. So this is big endian. So here we can see that basically um we're going from top to bottom. So we're taking like the big end and we're going from top to bottom. So we're starting from the leftmost side. So the leftmost side meaning like the most significant um bytes. And it's store word again. So it's still 4 bytes. So now we have a different case. It's loading, so LDR SW, so load sign word. And load sign word means word is still 4, but it's gonna be stored in a way that kind of like preserves the sign. So if it's negative, you're gonna be able to tell that no matter how many bits it's gonna be represented with, and then if it's positive, you can tell that the sign is positive. So it can be both positive and negative, but we're more like the special case that's gonna probably come up on your exam is gonna be the negative case. So let's go here. Okay. So first, before worrying about the signs or anything, we're just gonna do the loading first. So the we're loading from the um contents of X10 after the following instruction is executed, big endian storage is used. So we're gonna load the values to X10. Um, so yeah, this is gonna work the same way. So we look at like this is X9, and then we move down 8 spaces, we come here. and then we're doing big endian, so we're going top down. And this is 4 bytes is gonna be represented all the way here, the 4 bytes, but then there is some here that are like empty space. So originally it was all zeros. Now you're filling in, 4 of the bytes with the data from X9, but there's still 4 bytes left. So is it gonna be like still zero, or is it gonna be something else? So if it was not signed word and just word, then it would have just been zero and it wouldn't be a big deal. But since this is signed word, we have to kind of think about the sign. So we do a process called sign extend. And for to do that, you basically consider like the most significant bit over here. So in this case, this is 9. There can be other cases where, like it's not 9, like it could be like 3 or something, but this is 9. So for 9, you represent it like uh, for 9, you represent it like this. I don't know what was going on with my keyboard right there, but so as you can see, like if we expanded this into like binary, the first one would be 9, and then 2 would be like 0, 0, 0, 0, 1, 0. Right? So, and then etc., etc. But we're just looking at the most significant one, and in this case, there's 1. So if there's 1, that means that sign it has to be extended to the rest of the bytes. So that means like this whole number is actually negative. So this is all represented using 2's complement, and you know that in 2's complement, if the most significant bit is 1, that means that it's a negative number. So even when we're representing it in more bits, we still have to maintain that. So that's why the rest of the numbers, so the rest of the uh the rest of the binary numbers are all gonna be 1, so it's gonna extend. So it's gonna be, if there's like 1, 2, 3, 4, 5, so there's like 20 bits beyond this, like in front of this, they're all gonna be ones like this. So that's 4 1 4 1, etc., etc., all the way here, and then here it's gonna be the rest of these. So that's gonna be like the whole binary string is gonna be like that, a bunch of ones and then the actual data. So if you wanna, convert that back to hex, what's that gonna be? So you know that all ones in hex means it's a F, right? So it's all gonna be a bunch of Fs. And then this is gonna be, like 9, 2, and whatever else. So, in the final data, that's how it's gonna look. So a bunch of Fs and then the actual data. So that's how you do the load signed word. And yeah, that's it. Hope you guys can watch this so that you don't feel that you got behind just because like I wasn't able to finish. But yeah.